All right, in chapter 2, we looked at the periodic table. We looked at converting moles into mass and particles. And we want to use that same kind of idea, and then we're going to extend that to look at molecules now. So in chapter 2, we looked at the atomic masses of elements and the relationships between particles and masses. We want to look at that same idea for compounds. And so we're going to develop an idea, and this idea has a bunch of different names and abbreviations, but they all mean exactly the same thing. Formula weight, formula mass, molecular weight, molar mass, they all mean exactly the same thing whenever you see them. Abbreviations FW, MW, MM. In my day, we called it formula weight. We decided along the way that, well, it's really not weight, it's mass. And so now the most common term you're going to see is going to be molar mass. But they all mean exactly the same thing. Lots of different abbreviations. I'll use formula weight because that was drilled into my head 1,000 years ago and it's stuck. So we're going to go with it. So formula weight is simply grams per mole. We're going to use the periodic table to calculate the relationship between grams and moles, just like we do with elements. And so we're going to start out by calculating the formula weight of a simple compound like water. So go to your periodic table, and we're going to do a little inventory of the elements. So water is 2 hydrogens and an oxygen. Again, the subscript defines the guy in front of it. And what you need to do is go to your periodic table and find the AMU value associated with each element. Go to hydrogen, and notice the number is 1.008. When you extract from the periodic table, I want 2 decimal accuracies enough. So for that hydrogen, I would go 1.01. Right? If you go 1.008, I'm not going to argue with you, but for me, I'm always going to do 2 decimal places. So I've got 2 hydrogens, each at 1.01. Multiplied gives me 2.02 as their contribution to the mass. Find oxygen. What's its value? David, you here today? Yes, David. What's the oxygen value? What do you see as the number under the symbol O? Gary. 16.00. Give me 2 decimal accuracies. All right, so I've got 1 oxygen at 16.00, and then I'm going to add both up, and I'm going to get 18.02 as my value. Now, I pulled it directly from the periodic table, so one possible unit set for this thing is AMU. And AMU is simply what the average weight of one molecule would be. All right, so 16.02 AMU works fine. On the lab scale, we'll be looking at grams. So on the lab scale, the unit will be 18.02 grams per mole. Either unit is fine. Remember, though, that you need a unit when you have a number. For the work we'll be doing for this set of problems, the gram per mole makes more sense. The AMU, reserve that if you're talking about the mass of a single molecule of the material. All right, so let's take a minute and look at an example. What is the formula weight of 10,2-phosphate? All right, so I need to go to the periodic table. Kennedy, what is the symbol for 10? Committing, that's one of those weird ones. In column, it's a weirdo, column 4A. 10 is SN. So 10 is the symbol of SN. And what does that little Roman numeral 2 tell us? That tells us that the charge of the 10 is 2 plus. Okay, 10's in the oddball column, so he's going to need a Roman numeral structure. Then I see phosphate. 8 always tells me up polyatomic ion. I go to the polyatomic ion table, and I see that phosphate is PO4 with a charge of 3 minus. So first I need to develop a formula, and so I'm looking at that. Now, is this thing balanced as written, Allie? No, what do I need to do? I need to interchange charges with subscripts. When I do that, I get SN3, and because I need multiple polyatomics, I'm going to put it in parentheses, PO42. All right, so that is the formula of the material that I'm looking for. Now I want to set an inventory up. So my inventory tells me I need 3 10s, whatever that is. And now when I have something in parentheses, the subscript defines everything on the inside. So I have 2 phosphorus, and I have 8 oxygen. All right, so 310, 2 phosphorus, 8 oxygen. So now I need to go to the periodic table and look up the values. For 10, I've got 118.71. For phosphorus, I'm looking at 30.97. And in oxygen, we said earlier, we're 16.09. All right, so punch those numbers up, and I get 356.13 and 61.94 and 128. Add them all up, and my answer turns out to be 546.07. Now we need a unit for that. The unit can either be AMU or it can be grams per mole, but you need a unit. So either one is fine. Okay, so do you see what we've done in terms of our working with this inventory? Okay. Look at the next one. Aspirin has a formula with C9H8O4. Let's find its formula weight. C9H8O4. We're going to do it the same way we did it before. We're going to do a little inventory. For carbon, I've got 9. For hydrogen, I've got 8. For oxygen, I've got 4. I'm going to look up each one in the periodic table. And for my carbon number, I'm looking at 12.01. For hydrogen, 1.01. Again, extracting into 2 decimal places is good enough. And for oxygen, I'm looking at 16.05. Multiplying those across, I get 108.09, 8.08, and 64. We'll gather all our terms together. And again, 2 decimal accuracy on all numbers extracted from the periodic table. I'm getting 180.17. I need a unit. I can use AMU, or I can use grams per mole. 180.17. Questions about that? Now we're going to use it. We're going to use it in the way that we used it when we talked in chapter 2 about converting materials to moles. If there are 500 grams of aspirin in a sample, how many moles of aspirin do we have? So if I consider my known and my unknown, my known was mass of aspirin, and my unknown in this problem is moles. And looking back at the mole math, to go from mass to moles, one step will do it, and I need the formula weight of aspirin, which I've already calculated, 180.17. So I'll start off with my known material, 500 grams of aspirin. Again, my known material is always fully defined as a number, a unit, and an identity. And now I've got formula weight as my single step that does my conversion. And my conversion is set up so that whatever I have as my unit of my known becomes the denominator of the conversion factor. If I'm going to use formula weight, it has a standard setup of grams per mole. In these conversions with moles, I always put a 1 in front of the mole. So the gram number I calculated for aspirin, which was 180.17, is going to go in the denominator. The grams will now cancel out, and I'm left with moles of aspirin. So let's pick up our calculators and punch. We got 500 grams divided by 180.17 grams per mole. 366 is enough, unless you're told otherwise. I'm looking at 2.78, and I need units. Moles moles of aspirin. Okay. Yes, ma'am.
Where did you get the 180.17?
When we just calculated the formula weight of aspirin in the last problem.
Okay.
Okay. So we're doing these sequentially. We're building on each one. So that's where we got the 180.
Okay.
Okay. Alright, so calculated that. We got our 2.78 moles. Now, building further, how many molecules of aspirin are present in example 13? Well, with 13, we went from moles. 14, we're going to go to mass again this time. And so now, my new known, each project has its own known. My new known is moles of aspirin. And my new unknown is particles. And particles of a compound are molecules. So we're solving for molecules here. So my fully described initial condition, again, my mole map tells me the bridge between moles and particles is Avogadro. And so my fully described initial condition is 2.78 moles of aspirin. And my mole map tells me I can do it in one step, where moles in the known position puts me moles in the denominator of the conversion factor. I want to go to molecules because the smallest particle of a compound is a molecule. And the conversion factor is Avogadro. In these conversion factors, the mole gets the 1, and Avogadro's 6.022 times 10 to the 23rd is going to go up on top. Moles cancel out, and that's going to give me molecules of aspirin. So let's punch that up. 2.78 times 6.022 times 10 to the 23rd. 3 sig figs again. I'm getting 1.67 times 10 to the 24th. I need a unit. Molecules this time, because I'm looking at particles of my aspirin material. The mole map is giving me that in one step, 1.67 times 10 to the 24th, molecules of aspirin. Questions about that? We built sequentially through the problem. We started with mass, we converted to moles. From moles, we converted to particles, just like we did when we looked at just considered elements. Now, how many hydrogen atoms, how many atoms of hydrogen are present in 1.67 times 10 to the 24th molecules of aspirin? Well, a molecule is like the donut box. And when I open the lid of the donut box, I look in and see the individual element donuts. And in the aspirin donut box, what did we have? We had 9 carbon donuts and 8 hydrogen donuts and 4 oxygen donuts in every molecule. So, if we've got 1.67 times 10 to the minus 24th molecules of aspirin, how many hydrogens are in each molecule? Jake? How many hydrogens are in an aspirin? Just look at the formula. 8. So all I need to do is multiply by 8. And I can set up a little conversion factor just like before. But this one's nice and straightforward. My initial condition, 1.67 times 10 to the 24th molecules of aspirin. I want to know how many hydrogen atoms are in that molecule. So as the formula tells me, I have an 8-to-1 ratio. So there are 8 atoms of hydrogen per molecule of aspirin. Again, the name tells me there's the 8-to-1 ratio. I set my conversion factor up so that molecules of aspirin cancels out, and I'm left with atoms of hydrogen. So all I have to do is multiply by 8. And so I get 1.34 times 10 to the 25th atoms of hydrogen. So we're just doing a little inventory at the very end. We found particles of a compound, but I want to know what's happening on an atom basis. so I do a little inventory. All right, so let's try one more. How many atoms of hydrogen are in 10 grams of water? We're going to solve this problem in the 4 steps that we just looked at. Same way that we did. So my known this time is 10 grams of water. And my ultimate unknown is atoms of hydrogen. All right, when we worked this problem before, we did a couple of steps. So the first step, we took our fully established known, so I started with 10 grams of water. Now, I start with mass, and we already calculated the formula weight of water. That was 18.02. We did that in a previous example. So grams in the numerator means grams in the denominator. And I'm going to use formula weight according to the mole map. I'm looking at grams per mole. Mole gets the 1. We calculated the formula weight earlier to be 18.02. So what have we done now? We've canceled out grams, and now I've got moles of water. Our next step, using our mole map, get rid of moles. And I'm going to use Avogadro, so that's going to take me to particles. And again, in this conversion factor, the 1 that's in front of the mole, and particle conversion, Avogadro, 6.022 times 10 to the 23rd. So the moles cancel. I'm left with particles of water. I didn't want particles of water, I want atoms of hydrogen. So now we finish up with our inventory. We cancel out particles of water, and I bring atoms of hydrogen on board. How many hydrogens are in a water molecule? 2. So I'm looking at a ratio of 2 atoms of hydrogen, 1 particle of water. Particles cancel out, water cancel out, and I'm left, all my units are gone except atoms of hydrogen. So now I simply pick up and punch all the way across. 10 divided by 18.02 times 6.022 times 10 to the 23rd times 2. And I'm getting 6.68 times 10 to the 23rd atoms of hydrogen. So the mole map took you the 3 steps between mass and particles using formula weighted Avogadro, and the final step was simply inventory. How many atoms are in each compound? Questions about that? Yes, ma'am.
Can you go back to number 15? So why would you multiply by 8 instead of divide by 8 for the initial number?
All right, so the molecules of aspirin, that's the donut box.
Okay.
The question is, how many glazed donuts are in the box?
Okay.
I gave you 2 boxes of donuts. Each box has 8 glazed donuts in it. Did you divide by the 8? Or did you multiply by the 8 to give you the total number of glazed donuts? You multiply. Same idea here. 8 atoms, 8 glazed donuts in a box. The box is the molecules of aspirin. Right?
Okay.
Good question. All right, chemical compositions. We looked at this when we did the crucible lab. We figured out empirical formulas, so that's where we're headed now. So let's look at the chemical composition of some compounds. All right, let's start with the idea of the mass percent. And we did that as we made the magnesium oxide, and we figured out the mass percent of magnesium and oxygen in each by calculating the percent. The mass percent is simply the mass of each element in a compound as a percentage of the total mass. And so piece over total. All right, so let's figure out what the mass percent composition of methane would be, so methane is CH4. And the key to mass composition for a formula is the formula weight. I want to know the carbon component and the hydrogen component. So I need a formula weight composition. So I've got 1 carbon and 4 hydrogens. Go to the periodic table. Carbon is 12.01. Hydrogen is 1.01. Multiply those across. 1 carbon gives me a composition of 12.01. 4 hydrogens, I get a total contribution of 4.04. Add those together. I'm looking at 16.05 is the total contribution. And again, unit, either one is fine, A and U, or grams per mole. Now, to do the percent, it's part over total. And so for carbon, what's the composition? Carbon is 12.01 out of 16.05 times 100 to put it on a percent basis. And the hydrogen, similarly, 4.04 over 16.05. Put that one on a percent basis. All right, let's pick up our calculators and see what we got. 12.01 divided by 16.05 times 100. And again, 3 figs is enough. 74.8%. And then 4.04 divided by 16.05. I get 25.2%. And the thing we know about percentages, they better add up to 100. So when I add these two together, there's the check of my work. I get 100%. If you calculated the first one correctly, you could have found the second one simply by subtracting from 100. So that's how we calculate a simple mass percent. Let's repeat the activity. Let's find the mass percent composition of CH2O. We're going to do the same steps. We're going to find the formula weight first, and it's going to be the pieces over the total. So my material of interest this time is CH2O. I'm looking at the percentages. So what have I got? The formula's already built for. I've got 1 carbon, I've got 2 hydrogens, I've got 1 oxygen. I look up the formula weight of each piece from the periodic table. Carbon, 12.01. Hydrogen, 1.01. Oxygen, 16.00. Multiplying that across, 12.01, 2.02, 16.00. Gathering my terms. I'm getting 30.03, and I can use the unit of A and U. And now I need to convert everything into a percentage. And what I do to do that is I divide each piece by the total mass. So everything is divided by total mass, and then put on a percent basis by multiplying by 100. Now when I punch those up, 36 figs, 40.0%, 6.73%, 53.3%. And I gather my terms, I add everything together to check my work, and I see, indeed, I get 100. That's pretty straightforward. Did one of those in lab. Now, we also calculated empirical formula from lab. We did that with our magnesium oxide example. So we would have determined the empirical formula and molecular formula for mass percentages. All right? So here we go. A compound is found to have a mass percent composition as follows. It's 27.3% carbon and 72.7% oxygen. let's find this empirical formula. These are mass percentages. I want to do an empirical formula. Is an empirical formula based on mass or moles of material in the system? It's based on moles. Before I can do an empirical formula, I have to convert everything to a mole basis. All right, so my working information. I am 27.3% carbon, and I am 72.7% oxygen. All right, so first order business, these are percentages. I need to be working on masses and then moles. So what I'm going to do is I'm going to assume, make a nice and easy assumption. Assume I got 100 grams of material. Then immediately the percentages convert into grams. And so I'm working with 27.3 grams of carbon, and I'm working with 72.2 grams of oxygen. Now you could have made it any basis. You could assume 1 gram, you could assume 37.48 grams. The proportions would have been the same. Your final answer would be the same, but make a choice that's easy for you. So percent means out of 100, choose 100. Now I've got grams, and I want to go to moles. So what I need to do is I need to divide each guy by his own formula weight from the periodic table. So I look up carbon, and that's 12.01, and I look up oxygen, and that's 16.00, and the unit of both of these guys is grams per mole. And so the grams are going to cancel out, leaving me moles. So doing that calculation, 7.3 divided by 12.01, I'm getting, again, 3 sig figs are enough, 2.27, these are mole numbers, 2.27 moles, and for the oxygen, 72.7 divided by 16, I'm getting 4.54. Now, I want to build a formula at this point, but remember, I don't have 2.27 cows, I don't have 2.27 atoms. These are proportions. And before I build my formula, I need to have things in whole numbers. And so what I'm going to do to get whole numbers is I'm going to divide each guy by the lowest number of moles. And what that does is it creates a whole number ratio set. So 2.27 divided by 2.7 gives me 1. So the proportions in carbon, 1 carbon. And now if I do the second calculation, 4.54 divided by 2.27, I'm getting 2. So the proportions of carbon and oxygen in this compound are 1 carbon to 2 oxygens. And so that tells me that the formula, the empirical formula, is going to be CO2. So you find moles, you divide everything by the lowest, forcing somebody to 1. We need whole numbers when we build our formula. So that's how I do an empirical formula. So we convert percentages to mass, find moles, make mole ratios, and then build a formula. That's the empirical formula. Now, sometimes a compound is not an empirical formula. Sometimes it's a real compound, it's molecular, and it exists at a higher level. So the sample above, CO2 that I got from empirical, is known to have a formula weight of 132 grams per mole. So this is the real formula weight that comes from an outside source, some kind of experimental activity. So what is the formula weight of this, the molecular formula of this material? Well, what you're going to do is you're going to set up a ratio. If I have an ionic compound with proportions of 10 to 5, I know to reduce it to 2 over 1. What we're doing is we're reversing the simplification. So I need to know what the simplifying factor was. And to do that, I'm going to do a ratio of empirical formula to actual formula. So first order business is I need the formula weight of the empirical formula. All right, so in my inventory, I got 1 carbon, 12.01, 2 oxygens at 16, my CO2. I'm adding them up and I'm getting 44.01. So that is the empirical formula weight. So the ratio of the real formula weight to the empirical formula weight gives me the reduction factor. That's the factor by which I'm going to raise the 2 to 1 proportions. So I need the ratio of the known formula weight to the ratio of the empirical formula weight. And so I do a simple calculation. I divide 132, the real value, by the experimental value, 44.01, and I get a ratio of 3. Right? Now, what do I do with that ratio of 3? I multiply the empirical formula subscripts by that ratio. So rather than reducing it, I unreduce it, I multiply. So my CO2 empirical multiplied by the formula weight ratio raises all the proportions. C102 becomes C306. So if I've got an empirical and I want a real, I need the formula weight. I set up a reverse ratio to figure out how that's going to